Okay, here we go. We are still talking about calorimetry and energy flow. And in this video, this is a continuation of the previous video in that I'm going to define some things and make sure that we have the relationships and the vocabulary down. And what we are going to focus on in this video is heat and work. So in the last video, we focused on energy, the direction of the energy flow, and the fact that energy is conserved. And now we're going to talk about heat and work. Heat and work are two forms of energy. And when we talk about energy being transferred, these are really the two ways that can transfer energy. Heat is energy transferred by a change of temperature. In chemistry, we give heat, for some unknown reason, the symbol Q. Work is the energy transferred by movement, moving a piston, moving electrons, moving atoms. Work is given the symbol W. And our change of energy of a system, our delta E, is equal to the heat energy of that system plus the work energy of that system. And so we can't lose energy. We just have to move it around. And in our systems that we are talking about in chemistry, the two ways to move that energy around are heat and work. And so heat and work always have to add up to equaling our total energy. So heat energy, like I said, is given the symbol Q in chemistry. If the reaction is exothermic, that means that heat is leaving the system. Q is negative. If the reaction is endothermic, so remember exothermic, if we have system, the energy goes to the surroundings. This is the energy flow. The heat is leaving the system. If the reaction is endothermic, we have the opposite. We have the energy is entering the system. And Q is positive. Now, we tend not, for some reason in chemistry, we don't really talk about heat. We don't give it the name heat. Instead, we call it enthalpy. And so the change in heat during the course of the reaction is known as enthalpy, given the symbol delta H. So this is the heat final minus the heat initial is going to be your change in enthalpy. So work energy, this is a little bit more complicated. Work is given W. Work energy is the energy of moving something. And so we, as chemists, like to think of work as expansion work, taking up more space, or compression work, taking up less space. So an example of expansion work is when water evaporates. Wait, nope, that's not evaporating. When water breaks up into its atoms, where it splits water, and we get hydrogen gas and oxygen gas. So we're taking liquid water, which is compressed and not taking up much space, and we're making the gaseous diatomic molecules that take up lots of space. This is expansion. It is work done by the system. So this reaction is our system. And that system is taking up more space, acting on the surroundings. And so our convention is that, well, not really our convention, our definition of work is that work is equal to negative pressure times delta V, the change in the volume. So if the system is taking up more space, that means that this delta V, it's going to have a larger volume at the end than at the beginning. And so that delta V is positive, and that makes our work be negative. So expansion work is always going to be less than 0. Compression work is the opposite direction. It's taking the gaseous molecules and combining them into liquid water. And so that liquid water takes up less space. And so the delta V of the system is going to be negative. It's going to be less than 0 because the final condition takes up less space than the initial. And this means that work is being done on the system. And so you can think of this as the surroundings pushing in. And so in this case, work is always going to be positive because the delta V is negative. Okay, let's summarize that because this is rather confusing. We can get all these signs mixed up. I do all the time. Q is heat. If the system gains thermal energy, Q will be positive. If it loses thermal energy, Q will be negative. Work, W, if work is done on the system, work will be positive. This is compression. If work is done by the system, expansion, work will be negative. And if we put those together, the energy flows into the system. The delta E is positive. That is endothermic. If the energy is flowing out of the system, this is exothermic. Okay, so in the next video, I believe that we're going to start putting this together and start solving some problems. So I hope this helps give you a summary and starting to come up with the directionality of these signs. Do know that these sign conventions are for chemistry, and it's because of the ways that we have defined our variables. And so when you go to physics, these sign conventions sometimes are the same, sometimes are not the same. And that's just because the chemists and physicists think about their system and their surroundings in a different way. The chemist is very concerned about the perspective of the system. And we define everything from that perspective, and that gives us the sign conventions that I've presented here. Okay, hope to see you in the next one.